Welcome back to the Deep Dive. Our mission today is, it's pretty specific, but really, really crucial for anyone working with iOS. We are navigating well, let's face it, the complex, often intimidating world of modern iOS architecture and design patterns.
Exactly. And look, if you've ever felt just overwhelmed by that alphabet soup of acronyms, MVC, MVVM, Viper, TCA, this deep dive is designed to be your decoder ring.
Right.
We're not just going to define the jargon. The goal here is to really transform your understanding. So you go from knowing what these things are to knowing the fundamental why. Why do they exist? And maybe most importantly, when should you actually use them to get that right balance, between testability, scalability,
maintainability, all that good stuff.
All that good stuff.
And we've really dug deep for this one. We've compiled, an extensive stack of source material. It covers everything from, the historical core of iOS development.
Yeah, the very beginning.
Right up to the bleeding edge of modern state management. We're hitting the whole architectural spectrum. We'll start with MVC, of course.
Let's start there.
Move through MVVM, MVP, touch on the strictness of things like Viper and clean architecture. But we're also dedicating significant time to those foundational principles, the things that really underpin all good maintainable code.
Yeah, the building blocks, solid principles, dependency injection.
And those essential patterns, right? Structural, behavioral, the things architects use every day.
Exactly. But, our journey really has to begin at the common starting line, which honestly is also the source of probably almost every major scaling problem you see in mobile development. We absolutely have to address the pattern that Apple kind of naturally encourages and the massive headache it tends to create down the line.
Okay, let's do it. Let's unpack this. Yeah. We start with the absolute classic, Model View Controller, MVC. So MVC, it's been pretty much the standard in iOS since day one, right?
Yeah.
Largely because UIKit itself is so heavily built around that UI view controller concept.
Absolutely. It's baked in.
So in theory, what is MVC actually designed to do? What's the ideal scenario?
Well, the theory is pretty elegant, actually. MVC is a pattern designed specifically to achieve separation of concerns. The idea is to divide your application into 3 interconnected but, distinct components.
Separate jobs for each part.
Exactly. And theoretically, this means if you change the UI, you shouldn't have to touch your data handling logic. And vice versa. If the data changes, the UI ideally just adapts.
Okay, let's define those 3 roles really clearly, starting with the model. What's its job?
Okay, the model. This represents your application's data and, crucially, the logic specifically related to managing that data. So think your Swift classes, your structs, maybe core data entities, realm objects, whatever holds the actual information.
Right. The raw stuff.
The raw stuff.
Yeah.
And the source material really hammers this home. The model should be entirely ignorant of the UI, completely unaware.
Doesn't know about labels or buttons.
Zero idea. It's pure domain logic and data storage. So, a product model knows its price, its description, maybe inventory count, but it has absolutely no clue whether it's being displayed in a UI double view or some fancy UI collection view. Shouldn't care.
Okay, makes sense. Next up, the view.
The view. This is all about presentation. It's what the user actually sees and interacts with. So your UI labels, UI buttons, sliders, text fields, and, all your modern Swift UI views too.
And its job is purely display.
Strictly display and capturing input. The view is supposed to be, dumb is the term often used. It should contain 0 business logic. None. If you need to, say, take a date object and format it into a nice, user-friendly string.
Like 2 hours ago?
Exactly.
Yeah.
That logic does not belong in the view itself.
Okay, so model is data, view is display. And then we have the glue, the controller, which in classic iOS is almost always the UI view controller.
Yeah, that's the one. The controller's designated role, its intended role, is to be the mediator, the traffic cop, as you said earlier.
Right.
It listens for user input that the view captures, say, a button tap. It then goes to the model, fetches the necessary data, maybe does some basic processing on it if needed, and then it pushes the resulting state, the updated information, back onto the view so it can display it. It's the bridge between the data world and the visual world.
Okay, when you lay it out like that, it sounds like a really beautifully organized structure. Clear separation, easy to understand data flow. You could reuse models and views.
Yeah, the theory is sound.
But, and this is a big but, as pretty much any experienced iOS developer knows, The theory and the actual practice diverge pretty dramatically here, don't they?
Oh, massively. And it's largely down to the specific way Apple implemented MVC within the UIKit framework. See, the UI view controller isn't just a mediator. It's inherently coupled, deeply tied to the view's lifecycle.
Right, like view did load, view will appear.
Exactly. It's responsible for loading the view, handling screen rotations, managing memory warnings, dealing with navigation between screens, all this extra stuff.
So it's already got a lot on its plate before it even starts mediating.
Precisely. And that inherent link, that built-in responsibility set, causes the controller to just rapidly accumulate responsibilities that was never really meant to handle in the pure MVC pattern. Which leads us directly to #tag 1.2, the massive view controller MVC problem.
Yes. The infamous massive view controller, MVC, the bad kind.
Yeah.
I distinctly remember opening up a legacy project once. The main view controller file was so enormous, my IDE literally choked trying to index it. Had to be like north of 8,000 lines of code.
Oof. Yeah, I've seen those. We all have.
So what technically defines this architectural train wreck?
Well, technically, it's a UI view controller that has just grown way, way beyond its intended mediation role. It becomes this monolithic catch-all for everything. The sort of technical definition is any component that grossly violates the single responsibility principle. Usually this means it's handling like 5 or more fundamentally distinct functions.
Okay, what are the root causes then? Why does this happen so consistently? Why do developers, even good developers, inevitably end up here?
The sources really point to one main thing: overload by convenience. Because the controller is already managing the view lifecycle and connecting to the UI.
It's just the easiest place to put new code.
It's the path of least resistance, exactly. So it starts taking on more and more. You have 1, UI setup and view management, which, okay, that's part of its job.
Fair enough.
2, networking calls. Suddenly it's fetching data directly from an API. 3, data parsing and mapping, taking that raw JSON and turning it into model objects right there in the controller. 4, business logic, deciding what should actually happen when a user taps a button beyond just updating the UI. 5, sometimes even data storage or persistence logic, fiddling with core data or user defaults directly.
Wow.
And of course, navigation logic, knowing exactly which controller to instantiate and push or present next.
So yeah, instead of being this lightweight mediator, this traffic cop, it becomes the project manager, the network engineer, the data scientist, and the chauffeur, all rolled into one messy file.
Precisely. And the immediate consequence of that is disastrous tight coupling. The controller ends up manipulating models and views directly, often reaching deep inside them. Those clean boundaries just completely blur.
And that's where the pain starts, right?
Absolutely. Because when you have a single file responsible for both, say, handling network requests and configuring a table view cells, well, good luck writing tests.
Yeah?
You can't unit test the networking logic without somehow involving UIKit, which is slow and flaky, and you can't test the display logic without mocking out the entire network stack. It becomes a nightmare.
That complete lack of testability, the difficulty in maintaining it, the sheer terror of debugging it.
Yeah.
You know, that moment where you realize changing one innocent line of code in the networking block somehow broke a totally unrelated UI animation on the other side of the file. That's the pain point. That's what forces us as developers to seek out architectural evolution, to find better ways.
Exactly right. The fundamental need to maintain sanity, to reduce that crushing complexity, and, critically, to write robust, reliable unit tests that are independent of the UI frameworks. That's what spurred the adoption of these newer patterns that explicitly aim to pull that presentation logic and that data handling out of that overburdened UI view controller.
Okay, so if the core problem is the massive view controller, probably the most popular, most often cited modern solution, especially if you're working with reactive frameworks like Combine or RxSwift, is model view model, MVVM. Tag 2.1 MVVM, model view VM model, focusing on testability.
Yeah, MVVM really gained traction. Its core concept is the introduction of this new player, the view model. And the view model acts as the dedicated presentation engine for a view.
Okay, a presentation engine. So it's a separate component specifically designed to be testable, and it's completely decoupled from the actual UIKit view.
That's the goal, yes, completely decoupled.
So how does this view model actually separate the concerns more effectively than the controller did back in MVC? What's its specific job?
The view model takes over that critical presentation logic that used to clutter the controller. Its primary role, its main job, is to expose data from the model, but in a format that the view can consume directly with no further processing.
Okay, give me an example.
Sure. Let's say your model has a raw currency value, like just a double representing dollars, and maybe a date object for when a transaction occurred. The view model is responsible for taking that raw double and transforming it into a properly formatted locale-aware currency string, like 1999 cents, and taking that date and turning it into just now or yesterday. That transformation logic lives in the view model.
So it preps the data perfectly for display.
Exactly. It also often handles the complex state logic around the view, things like loading states, data fetching, error states, did the fetch fail, maybe managing the interaction with the network layer.
Okay, so the view model contains purely view-specific logic, but critically, it has absolutely no reference to actual UIKit elements like UI label or UI button.
That is the magic of MVVM, yes. No import UIKit in your view model file, ideally. The UI view controller, or the SwiftUI view, now becomes a much thinner view layer. Its only jobs are really setting up the actual UI elements and then observing the view model for changes.
That sounds like a key difference from MVC.
It's a massive shift in data flow. In MVC, remember, the controller imperatively told the view what to do. Hey view, set this label's text now.
Right, direct command.
In MVVM, the view model typically publishes changes to its state, often using reactive mechanisms, and the view simply subscribes or binds to those publications and reacts automatically whenever the data updates. It's a more declarative approach.
Okay, I have to push back a bit here, though. If the view model is handling network calls and data transformation, aren't we just shifting the massive problem from the controller to the view model? How does MVVM really enforce separation from, say, the networking layer?
That's a really crucial point, and something that good MVVM implementations address directly, usually through dependency injection, which we'll definitely circle back to later.
Okay.
A well-designed view model should not know about concrete networking classes like API Manager. Instead, it should depend on an abstraction, typically a protocol in Swift, maybe something like User Service Protocol.
So it asks for the capability, not the specific tool.
Exactly. The view model says, I need something that conforms to User Service Protocol. It doesn't care how that protocol is implemented. This is what keeps the view model truly testable, because during your unit test, you can easily inject a mock user service that just returns predefined data, completely isolating the view model's presentation logic from any real network activity.
Got it. That decoupling through protocols is key. Now let's talk about the practical side of that observation, that data binding. How does the view actually listen to the view model in modern iOS? Our sources mention three main ways.
Right. So the most sort of direct non-framework approach is using closures or callbacks. The view essentially gives the view model a block of code to run whenever a particular piece of data changes.
Like an on-update closure.
Exactly. var on user update, user void. It's simple, it's concise for basic cases, but if you have a complex screen with lots of changing data points, managing all those separate closures can get a bit messy and hard to track.
Okay. What's the more modern standard approach, especially since iOS 13?
That would definitely be Apple's Combine framework. Combine is the go-to reactive standard now. View models expose their data using app-published properties, and the view then subscribes to these publishers using operators like sync, or even more seamlessly in SwiftUI, by directly assigning them to the view's state variables. Combine is really powerful, it's natively supported, and it handles complex asynchronous data streams and lifecycle management quite elegantly.
Makes sense. And the third way, the sort of older, more traditional method.
That's key value observing, or KVO. It's been around forever in Objective-C and Cocoa. It works, but it's generally considered less type-safe and much more verbose than using Combine. You're dealing with string-based key paths, which are prone to typos, and the setup is just clunkier. It's less preferred in modern Swift development.
Okay, so pulling it together, MVVM seems fantastic when testability is a really high priority, when you're dealing with complex data transformations for the UI, and especially when you're already integrating with reactive paradigms like Combine or maybe RX Swift.
Yeah, that's a pretty good summary. It fits very naturally into that modern reactive iOS world. Hashtag TAC 2.2 MVP, Model View Presenter, the passive view.
All right, let's look at the other main evolution from MVC. Model View Presenter, or MVP. It takes a slightly different tack to achieve that necessary separation, really emphasizing this idea of the passive view.
Right. The passive view concept is central to MVP. The goal is to make the view as dumb or passive as technically possible.
So dumb it doesn't even know how to update itself based on new data.
Pretty much, yeah. In MVP, you introduce the presenter. The presenter takes on the responsibility for all the presentation logic and for actively driving the view.
How does it drive the view if the view is passive?
Through a contract, usually a protocol. The view conforms to an interface, maybe called User Profile View Protocol, which defines methods like display username, string, or show loading indicator.
Oh, okay.
The presenter holds a reference to the view only through this protocol. When a user taps a button, the view just notifies the presenter, hey, the save button was tapped. The presenter then does its logic, maybe talks to the model, figures out what needs to change, and then explicitly calls methods on the view protocol. Okay, view, call display success message now. The view just obeys commands.
The key advantage, always cited for MVP, often positioned as its biggest strength over even MVVM sometimes, is testability.
Absolutely. Because the presenter only interacts with the view via that protocol interface, the presenter itself has zero dependency on UIKit, none whatsoever.
So you can test it completely headless.
Exactly. You can instantiate the presenter in a unit test, give it a mock view, just a simple class conforming to the view protocol, simulate user actions by calling its methods, and then assert that the correct methods were called on the mock view. You can test the entire presentation logic flow without ever touching a UI view controller or worrying about the view lifecycle.
Okay, so MVP keeps the view incredibly clean, very passive, and makes the presentation logic super testable. What are the practical downsides or trade-offs? Why might a team choose MVVM instead?
There are usually two main drawbacks people mention. First, the boilerplate. You often end up defining a protocol for the view interface and sometimes another protocol for the presenter interface itself, plus the concrete classes. It just adds a bit more setup ceremony compared to, say, basic MVVM with Combine.
More files, more protocols.
Yeah, a bit more scaffolding. Second, the presenter itself isn't immune to becoming bloated. If you have a really complex screen with tons of state and intricate UI updates, the presenter still has to manage all of that state and issue all those imperative commands to the view. You solve the massive view controller problem, but you could potentially end up with a massive presenter problem if you're not careful. It doesn't inherently prevent logic accumulation in that one component. Hashtag TAC 2.3, choosing between MVC, MVVM, and MVP.
Okay, so if we kind of synthesize these three, the classic MVC and the two main evolutions, MVVM and MVP, what does the decision tree look like for a development team starting a new project or maybe refactoring an old one?
Well, let's be honest. If the application is genuinely tiny, like a simple utility app, or maybe a quick prototype that you know is never going to grow beyond, say, 5 screens.
A flashlight app.
Yeah, exactly. Or maybe a simple settings screen. MVC is the absolute simplest path. It requires the least setup. You might just accept the risk of future complexity if the scope is truly limited.
But as soon as things start to scale, or if testability becomes a serious requirement, which it should be.
Right. Then the choice really boils down to MVVM versus MVP.
Okay. How do you pick between those two?
MVP is probably ideal if you need guaranteed, straightforward testability above all else. And maybe you prefer a more traditional imperative programming style where the presenter explicitly tells the view what to do, step by step. It also avoids the learning curve that sometimes comes with reactive frameworks like Combine.
Of MVVM.
MVVM is often considered the modern sweet spot, especially now with how mature Combine is and how SwiftUI embraces declarative UI. MVVM becomes the more logical choice when your application naturally deals with lots of asynchronous data streams, complex state interactions, and when you want that seamless data binding. It just meshes really well with the way modern iOS apps are often built.
So it sounds like while MVP offers simpler testability perhaps, MVVM provides that flexibility and the powerful data binding capabilities that fit better with complex, asynchronous modern apps. Even if there's maybe a slightly steeper initial learning curve, getting comfortable with Combine or RX Swift.
I think that's a fair assessment, yeah. The upfront investment in learning those reactive concepts often pays off significantly in terms of managing complex state more effectively later on in the project's lifecycle.
Okay, so we've explored patterns like MVVM and MVP that primarily focus on refactoring that problematic controller. But what about situations where you need to manage complexity on a truly massive scale? Huge enterprise projects, maybe hundreds of thousands of lines of code, dozens of developers working over years. That demands maximum separation of concerns, right?
Yeah, absolutely. For those scenarios, you often move into architectures where modularity and ensuring every single component has only one very specific responsibility become the absolute top priorities. Hashtag tag 3.1 VIPER, View Interactive Presenter Entity Router.
Which brings us to VIPER. That acronym itself sounds serious. View Interactive Presenter Entity Router. It feels like the quintessential structure if you're aiming for maximum single responsibility. It takes the typical 3-part structure and just explodes it into 5 distinct layers.
That's a good way to put it, yeah. Viper's absolute goal is to ensure that no single component ever wears more than one hat. It enforces a very strict, often cyclical, flow of data and control between these 5 parts, relying heavily on protocols to define the boundaries and enforce that structure.
Okay, let's break down those 5 layers. How do they map or differ from what we saw in MVVM or MVP?
Okay, starting with the view. Just like an MVP, it's intended to be very passive, deals only with displaying UI and capturing raw user input, nothing more.
Got it. Then the interactor. That's a new one?
Right. The interactor is purely about business logic. This is where the core application rules live for a specific feature or use case. It fetches and manipulates data, often working with entities and coordinating with external services, like networking or databases. Critically, the interactor knows absolutely nothing about how data is presented or how the user navigates through the app. It's pure logic.
Okay, so view is UI, interactor is business logic.
Yeah.
Then the presenter. We've seen that name before.
We have, but its role in Viper is slightly different, maybe more focused than in MVP. The Viper presenter is really the traffic controller for the UI side. It receives user actions forwarded from the view. It then tells the interactor, hey, perform this business logic. It receives the resulting data back from the interactor. Then, importantly, it translates that raw data, often entities, into simpler presentation models suitable for the view. And finally, it sends the specific display commands back to the view. So it's the bridge, converting domain-level results into UI-level concepts.
Okay, and the data itself, the entity.
Entities are just the pure data models, often simple Swift structs or plain classes. They carry the core business information but contain zero UI logic, zero flow logic, nothing specific to the application's features, just the raw business objects like user, order, product.
And the final piece, the one that explicitly tackles navigation complexity, the router.
Yes, the router, sometimes also called the wireframe. This component's sole job is handling navigation between different Viper modules or screens. It essentially knows the map of the application, how you get from the login screen to the dashboard, or from the product list to the product detail.
So when the presenter decides navigation needs to happen,
It doesn't do it itself. It delegates that entire task to the router. The router is responsible for instantiating the next Viper module, view, interactor, presenter, router for the next screen, and handling the actual transition, pushing, presenting, etc. This is vital because it keeps the view and presenter completely focused just on the content and logic of the current screen.
the appeal here is undeniable, right? Extremely high modularity, maximum testability for each individual component, and it seems like it would scale incredibly well for large teams and complex apps. But let's be really blunt about the trade-off.
Well, the trade-off is significant, and it's complexity. Specifically, setup complexity, boilerplate,
Right.
the so-called Viper tax.
Right.
For even a relatively simple feature, you often end up creating 5 separate classes: view, interactor, presenter, entity, router, and probably at least 5 corresponding protocols to define the interfaces between them. That's a lot of files and setup code just to get started.
So why? Why would an enterprise application choose to pay that heavy Viper tax? What's the long-term payoff?
The sources explain this quite well, actually. That heavy upfront investment in protocols and strict separation is seen as a down payment on long-term bug reduction and maintainability. Think about it. 6 months down the line, a new junior developer joins the team and needs to change how data is fetched for a particular screen. Because of Viper's strict structure and protocols, they know they only need to look inside the interactor for that module.
The boundaries are super clear.
Crystal clear. The enforced isolation ensures that changes made inside the view cannot accidentally break logic inside the entity, and changes in the interactor won't unexpectedly mess up the navigation handled by the router. It significantly reduces the chance of those dreaded unexpected side effects. Plus, it arguably makes onboarding new team members easier because the system is so rigidly structured and predictable, even if initially complex. Hashtag tag 3.2, the coordinator pattern delegating flow.
Okay, speaking of complexity and navigation,
Yeah.
even if you're using a more moderate pattern like MVVM, that navigation logic can still start to creep back into the view controllers, right? Making them sort of massive again, but this time just for managing the application flow.
Absolutely. That's a very common pain point.
And this is where the coordinator pattern comes in. It seems like it essentially borrows that router concept from Viper, but allows you to apply it more selectively.
That's a perfect way to think about it. The coordinator pattern specifically targets the problem of navigation logic polluting view controllers or view models without forcing you to adopt the entire heavy Viper stack. It extracts all responsibility for application flow management out of the individual screen components.
Okay, how does it work in practice? What does a coordinator actually do?
You create a dedicated coordinator object. This object typically owns or manages one or more related view controllers. When a UI view controller needs to navigate somewhere, say, a user taps the checkout button in a shopping cart screen, that view controller doesn't directly instantiate and push the next screen itself.
It doesn't call navigation controller.push view controller.
No, instead it delegates that request back to its owning coordinator. It might call something like coordinator.didTap checkout with cart items. The coordinator then takes over. It decides which view controller to show next, the payment screen maybe, how to configure it, passing in the cart items, and handles the actual presentation logic, whether to push it onto the navigation stack, present it modally, or maybe even dismiss the current flow entirely.
So the view controller's only job related to flow is basically just to signal outwards, hey, something happened that requires navigation.
Exactly, just reporting events. The benefits here are pretty substantial. First, it drastically reduces the complexity and size of your view controllers. Second, it centralizes all the navigation logic for a specific feature or flow into one place, the coordinator making that flow much easier to understand, test, and debug.
And reuse.
And improves reusability significantly. You can take a fully functional, self-contained profile view controller and just drop it into a completely different part of the application, managed by a different coordinator, because the view controller itself has zero baked-in knowledge of how to navigate away from itself. It's much more plug-and-play. Hashtag tag 3.3, clean architecture, the onion.
All right, so if Viper focuses heavily on separating the components of a single feature or screen, clean architecture seems to take a broader view. It looks at the dependencies across the entire application, visualizing it as these concentric layers. The onion analogy.
Exactly. Clean architecture, heavily influenced and popularized by Robert C. Martin or Uncle Bob, has a very specific core idea. The business rules, the absolute heart of your application, the logic that makes your app unique and valuable, must be completely independent of the infrastructure details.
So what structure like
the UI framework, UIKit or SwiftUI, the specific database you're using, Core Data, Realm, Firebase, the networking library, any third-party frameworks, all the external stuff.
And the fundamental rule that governs this onion structure.
The dependency rule. Dependencies must always point inward. The inner layers, containing the most fundamental business rules, must know absolutely nothing about the outer layers. However, the outer layers are allowed to know about and depend on the inner layers.
Why is that so important?
It ensures that your core domain logic, the real essence of your application, can potentially survive massive technological shifts. If you decide to switch from UIKit to SwiftUI or from core data to a cloud database, your innermost layers, containing the core business rules, ideally shouldn't require any changes.
Okay, let's walk through those layers, typically shown as 4, starting from the very outside and moving in.
Right. On the absolute outside, you have frameworks and drivers. This is the implementation layer. This is where your concrete UI code lives, UIKit, SwiftUI, your actual database access code, your networking clients like URL session, device interfaces, and any third-party libraries you integrate. It's the most volatile layer.
Okay, moving one layer in.
We find the interface adapters, sometimes called the presentation layer. This layer acts as a set of converters or adapters. Its job is to translate data between the format most convenient for the inner layers, the use cases and entities, and the format most convenient for the outer layer, the frameworks and drivers.
So this is where things like view models or presenters would live.
Exactly. View models that format entity data for the UI, presenters that orchestrate UI updates, maybe data mappers that convert network responses into domain objects, they all belong here. They adapt the inner world to the external frameworks.
Okay, layer 3, getting closer to the core.
This is the use cases interactors layer, often called the application layer. This layer contains the application-specific business rules. It defines what the application does. It orchestrates the flow of data to and from the entities to achieve specific goals.
Give me an example of use case.
Sure. A complete order use case. It would define the exact sequence of operations. Check product inventory using entities, process payment, delegating outwards, perhaps via an interface adapter, update the order status in an entity, maybe trigger a notification, again, delegating outwards. It dictates the workflow, but it's still independent of the UI or database specifics.
And finally, at the absolute center, the protected core, the entities, also known as the domain layer.
Yes. These are the most fundamental building blocks. They encapsulate the enterprise-wide business rules and the core data structures. These are typically pure Swift structs or classes containing logic that is intrinsic to the business itself, regardless of the application. For example, a rule like an order total must always be positive, or a user must have a valid email address. This logic should ideally never change just because you switched your UI framework or database provider.
So the ultimate benefit of embracing clean architecture is achieving true framework independence for your core logic. You could, theoretically, write your use cases and entities once, test them thoroughly in isolation, and reuse that core across an iOS app, an Android app, maybe even a web backend, with only the outer layers needing to be rewritten.
That's the dream, yes. It maximizes testability, maintainability, and the potential for refactoring or even complete platform migrations because the most valuable part of your code base, the business logic, is decoupled and protected.
Okay, so we've covered these big structural patterns like Viper and clean architecture, which are great for organizing code and dependencies. But a huge chunk of complexity in modern apps, especially reactive ones, really revolves around managing state, right? Tracking asynchronous data fetches, user interactions, side effects. It gets complicated fast.
Oh, absolutely. State management is often where things fall apart if you don't have a good system.
And this has led to the rise of newer, more opinionated paradigms. Probably the most talked about one in the Swift community right now is the composable architecture, or TCA.
Yeah, TCA, developed by the folks at Point Free, has gained a lot of traction. It's a powerful Swift library, but it's definitely an opinionated approach. It draws heavy inspiration from functional programming concepts, particularly from things like Redux in the JavaScript world and the Elm architecture.
And its main goal is
predictability and consistency. It enforces a very strict unidirectional data flow, aiming to make application state changes easy to understand, easy to test, and highly composable.
Okay, you said it's structured. Let's break down the 4 key components that define TCA and make it so predictable. What are they?
Right. So first, you have the state. Now, unlike MVVM, where your state might be spread across several at published properties in a view model, TCA generally pushes you towards having a single centralized state struct for each feature, and sometimes even for the entire application state. All the data that feature needs to function lives in this one immutable value type.
One source of truth for the data.
Okay.
Second,
the action. This is crucial. The action is typically an enum that explicitly models every single possible event that can occur within that feature or system.
Every event, like every button tap.
Every button tap, every text field change, every response received from a network request, every notification from the system, every timer tick. If it can change the state or trigger a side effect, it needs to be modeled as an explicit case in your action enum.
Wow, okay, that sounds comprehensive.
It is, and that explicitness is what gives TCA a lot of its power for debugging, logging, and even time travel debugging, because you have a perfect audit trail of everything that happened.
Okay, state holds the data, action represents events. Third component.
The reducer. The reducer is really the brain of a TCA module, and critically, it's defined as a pure function. This is a really important concept, especially for developers coming primarily from an object-oriented background.
Explain pure function in this context. Why is that such a big deal?
Okay, a pure function has 2 main properties. 1, given the same inputs, it will always return the exact same output, no exceptions. 2, it has no side effects, meaning it doesn't modify any external state, doesn't perform network calls, doesn't write to disk, doesn't print to the console.
So how does that compare to, say, a method in a typical view model?
Well, think about a standard view model method, maybe viewModel.loadUserData. When you call that method, it might internally check if the user is logged in. Maybe it depends on the current network connectivity status. Maybe it interacts with a shared cache. Its behavior could potentially change depending on all sorts of external hidden states.
Right, it's not deterministic.
Exactly. A pure reducer, on the other hand, is completely deterministic. Its signature is basically in-out state, action, effect. Given a specific current state value and a specific action case, the reducer must produce the exact same resulting state every single time you call it. Any interaction with the outside world, any asynchronous work is handled separately.
Okay, so how does it handle that outside world stuff, like network calls? That brings us to the 4th component.
Precisely. That's where the store and effects come in. The store is the runtime object that actually holds the current state, sends actions to the reducer, and drives the UI updates. Effects are TCA's way of modeling and managing side effects, those non-pure operations, like making network requests, reading from user defaults, starting timers, interacting with core location, etc.
So the reducer itself doesn't do the network call?
No. When the reducer processes an action, like .fetch button tapped, it might update the state, for example, set iLoading true. But instead of performing the network call directly, it returns an effect value that describes the work to be done, like .fetch user data effect.
Oh, okay.
The store then takes this effect description, executes the actual asynchronous work, like the network call, and when that work completes, either successfully with data or with an error, the result is fed back into the store as a new action, e.g. .userDataResponse, .successUserData, or .userDataResponse.failure error.
So the cycle remains closed and pure. The reducer only deals with state transitions based on actions.
Exactly. It keeps the core state mutation logic perfectly deterministic, side effect free, and therefore incredibly easy to test.
Okay, so for a developer who's maybe comfortable with the flexibility of MVVM using Combine, what's the biggest philosophical leap or hurdle when trying to adopt TCA?
I'd say the biggest shift is towards centralization and explicit rigidity. In MVVM, you typically manage state using multiple @publish properties scattered within your observable object view model. The view observes these. It's quite flexible, very object-oriented, and you handle logic by calling methods directly on the view model.
Right.
In TCA, state management is strictly centralized into that single state struct. And all state mutations must happen synchronously within the reducer, triggered only by explicit action enum cases. You don't call methods to change state, you send actions.
That difference in handling actions versus methods seems like it would have a massive impact on testability.
Huge impact. Testing a typical MVVM view model often involves instantiating the view model, maybe injecting some mock dependencies like network services, calling its methods, and then asserting that its internal @publish properties change to the expected values. You might need to manage asynchronous expectations if it kicks off Combine publishers.
Okay. And testing a TCA reducer.
Testing the core logic in TCA is radically simpler. You just test the pure reducer function. You create an initial state value, you create an action enum case, you pass them to the reducer function, and you assert that the state value after the function returns is exactly what you expect it to be. That's it.
No mocking.
No mocking of time, no mocking of network layers, no dealing with asynchronous expectations for the core logic, because the reducer itself is pure and synchronous. Testing the effects, the side effects, is handled separately, often using specialized testing tools provided by the TCA library that allow you to assert that the correct effects were returned and that they feed back the expected actions.
And that handling of side effects, which, let's be honest, often clutters up view models in MVVM, is now completely externalized and managed explicitly as effects in TCA.
Correct. When the reducer processes an action like, say, .user tap save button, it doesn't attempt to write to the database itself. It updates the state optimistically, maybe sets a saving true, and returns an effect like .save user data effect user data. The store runs that effect, the effect performs the actual database write, and the result, success or failure, comes back as another action, keeping the whole cycle clean and testable at each step. Hashtag 4.3 challenges of adopting TCA.
Okay, the predictability, the testability. It really does sound like an architectural nirvana in some ways. But we know there's no free lunch. TCA definitely comes with costs. What's generally considered the biggest barrier to adoption?
I think the primary one is the steep learning curve. It's not just learning a new library, it requires really embracing a functional programming mindset. Concepts like pure functions, immutability, algebraic data types, enums for actions, and managing side effects explicitly as effects. It's a significant mental shift from traditional object-oriented development in Swift. It changes how you fundamentally think about structuring application flow.
And I've definitely heard the boilerplate discussion comes up even more intensely with TCA than with Viper sometimes.
It can feel that way, yes. The verbosity is definitely higher. Even for a seemingly simple screen like a counter, you need to define the state struct, the action enum, with cases for increment, decrement, maybe a timer tick, and the reducer function. Often these end up in separate files.
So lots of setup for small things.
Yeah. Every single user interaction, every potential state change, every possible asynchronous result needs to be explicitly modeled as an action enum case. That initial setup can feel quite burdensome, especially when you're just trying to build a small feature quickly. It front loads a lot of the structural thinking.
And the final point, which is always consideration with non-Apple frameworks.
Right. The ecosystem dependency. TCA is a fantastic, well-maintained, and popular third-party library. But adopting it means you are committing your application's core architecture to an external dependency, rather than relying solely on Apple's native frameworks like Combine and SwiftUI, which MVVM leans on more directly. That's a strategic decision teams need to weigh.
So it sounds like while MVVM often hits that flexible sweet spot, TCD is more like a deliberate, high-commitment choice you make when your application reaches a certain scale of complexity and you absolutely need guaranteed long-term state predictability and testability above all else.
That's a very good way to characterize the trade-off, I think.
Okay, so we've toured through all these different architectural patterns, MVVM, Viper, TCA, clean architecture. But regardless of which high-level blueprint you choose, the actual success, the maintainability of your architecture, really hinges on the underlying software design principles you follow day to day in your code.
Absolutely. The architecture gives you the structure, but the principles guide the quality of the implementation within that structure.
And the most crucial, most cited set of principles for building flexible and maintainable, object-oriented, and even protocol-oriented systems is encapsulated by that acronym.
Solid.
Yeah, solid. Developed largely by Robert C. Martin again. These 5 principles provide the foundational guidelines for writing code that doesn't just work now, but remains flexible, understandable, maintainable, and testable months or even years down the road. They are absolutely key to avoiding that massive view controller problem we started with. Hashtag 5.1, the value of solid principles.
Let's zero in on the S first, the single responsibility principle, SAFRP. This feels like the most direct answer to the original MVC flaw we discussed. It really is. SRP states that a class or struct or module should have one and only one reason to change. If you find yourself modifying your UI view controller because the UI layout needs adjusting, and you're also changing it because the format of the API response changed, and maybe because the navigation destination changed, that class clearly has multiple reasons to change. It's violating SRP.
So applying SRP is basically the act of breaking down those monolithic components.
Exactly. It's the most effective first step in refactoring. If you find API parsing logic inside your view controller, SRP tells you that logic doesn't belong there. Its reason for changing API format is different from the view controller's primary reason for changing UI presentation or user interaction handling.
So where should that API parsing logic go?
It needs to be extracted into a separate, dedicated component, maybe an API service class or a user data parser struct, something whose single responsibility is dealing with that specific task. The view controller's responsibility then shrinks back towards just mediating between the UI and maybe a view model or presenter. This isolation immediately makes your new API service independently testable.
Okay, SRP is about breaking things down. Let's jump ahead to the dependency inversion principle, DIP. This one seems vital for achieving decoupling and enabling effective testing.
Absolutely critical. DIP has 2 parts, but the core idea for us here is that high-level modules, like your view controller or view model, should not depend on concrete low-level implementations, like a specific Firebase database manager class. Instead, they should depend on abstractions, which in Swift usually means protocols.
So if my view model needs to fetch user data, it shouldn't directly import and instantiate Firebase database manager.
Correct. According to DIP, it should instead declare that it needs something conforming to a user data fetching protocol. The view model only knows about the abstract interface defined by the protocol. Example, a fetch user string method. It has no idea whether the actual object fulfilling that protocol talks to Firebase or core data or just returns mock data.
Why is that distinction, depending on the protocol, not the concrete class, so powerful?
Because it completely decouples the view model from the specific data fetching mechanism. During development and production, you might inject the real Firebase database manager, which conforms to user data fetching. But during unit testing, you can effortlessly inject a mock user data fetcher, which also conforms to the same protocol, without changing a single line of code inside the view model.
Makes testing trivial.
Exactly. It's the cornerstone of testability and also extensibility. If you later decide to switch from Firebase to your own backend, you just create a new MyBackend user data fetcher class that conforms to user data fetching and inject that instead. The view model remains untouched. It allows you to swap out core components cleanly.
We should probably briefly mention the other 3 solid principles, as they also play a role in managing complexity. Let's start with open closed.
Right, the open closed principle, OCP. This states that software entities, classes, modules, functions should be open for extension, but closed for modification. The idea is you should be able to add new functionality without changing existing working code.
How do we achieve that in Swift?
Often through protocols and default implementations or class inheritance, though composition via protocols is often preferred in Swift, or extensions. A classic example is payment processing. You define a payment processor protocol with an execute payment method. You have concrete classes like credit card processor and PayPal processor conforming to it. If you later need to add Apple Pay, you just create a new Apple Pay processor class conforming to the protocol. You extend the system's capabilities without ever modifying the original tested credit card processor or PayPal processor code.
Makes sense. Okay, what about the LNI, Liskov substitution and interface segregation?
Sure, the Liskov substitution principle, LSP, is a bit more theoretical sometimes, but essentially says that subtypes must be substitutable for their base types without altering the correctness of the program. If you have a function that works with a Berg protocol, it should work correctly whether you pass in a sparrow or a penguin. Even though penguins don't fly, the program shouldn't crash or behave unexpectedly if the Berg protocol was designed correctly. Swift's strong type system and protocol conformance help enforce this to some extent.
Okay. And ISP, interface segregation.
The interface segregation principle, ISP, is often more practically relevant in day-to-day iOS development. It states that clients, classes using an interface, should not be forced to depend on methods they do not use. In other words, interfaces should be small and focused rather than large and monolithic.
How does this typically get violated in the UIKit world?
The classic example is the giant UItable view delegate protocol. It has dozens of methods for handling row selection, editing, headers, footers, accessory view, scrolling. Your specific UI view controller might only care about one single method, maybe tableview.selectRow it.
Right.
But by conforming to the whole UItable view delegate, your class is technically coupled to and aware of all those other methods it doesn't even use. This violates ISP. The solution, especially if you find yourself implementing many delegate methods, is often to break that responsibility down. You might create smaller helper objects that conform to just the specific parts of the delegate protocol they need, like a separate table view editing handler, keeping your view controller cleaner and adhering better to ISP. Hashtag TagShack 5.2 dependency injection, DI.
Okay, so that dependency inversion principle, DIP, depending on abstractions protocols, leads us directly to the practical mechanism that makes it work. Dependency injection, or DI. You mentioned it earlier. Why is DI considered so essential for professional, scalable iOS development?
Yeah, DI is really the engine that powers DIP. It's the practice, the technique, where an object receives its dependencies, the other objects it needs to work with, from an external source rather than creating them itself internally.
So instead of a view model having a line like let network service, real network service, inside its init.
Right. That network service instance is provided to the view model from the outside when the view model is created.
And why is this non-negotiable for serious projects?
Because it solves the tight coupling problem we keep circling back to, the one inherent in naive MVC. If a class creates its own dependencies internally, it's inherently tied to those specific concrete implementations. You cannot test that class in isolation without also bringing along all its self-created dependencies.
What if it receives them?
If it receives them from the outside, it's decoupled. It doesn't know or care how those dependencies were created, only that they conform to the required protocol or type. This decoupling is what unlocks easy mocking and stubbing during unit tests. You can provide fake dependencies that return predictable data, ensuring that your test is focused solely on the logic of the class under test, not its collaborators. It dramatically enhances testability, which in turn boosts maintainability and scalability.
Okay. Our sources mentioned 3 primary ways, or mechanics, for actually performing DI in Swift. Let's start with the most common and usually preferred method, constructor injection.
Yeah, constructor injection or initializer injection is definitely the gold standard in Swift. Dependencies are passed directly into the class's init method as parameters.
Network servicing, database protocol, like that.
Exactly like that. The massive advantage here is twofold. First, the dependencies are guaranteed to be non-nil and available right from the moment the object is fully initialized. The object simply cannot exist in a valid state without its required dependencies being provided. Second, you can often store these injected dependencies as immutable constants let within the class, which prevents them from being accidentally changed later, eliminating a whole category of potential runtime bugs. It makes the class's requirements explicit right in the initializer signature.
Okay, overwhelmingly preferred. But what about the second type mentioned? Property or setter injection?
Property injection, sometimes called setter injection if you use a dedicated setter method, involves creating the object first, often with a default initializer, and then assigning its dependencies to mutable properties after it's been created.
So let view model, followed by viewModel.network service, real network service.
Precisely. This approach offers more flexibility. It's useful for dependencies that are truly optional or sometimes necessary when working with frameworks like older UIKit patterns with storyboards that might instantiate objects for you using a parameterless initializer, not allowing you to use constructor injection easily.
Well, but what's the downside of that flexibility?
The downside is that the dependency is no longer guaranteed to be there. The property might be nil at runtime if someone forgets to set it after creating the object, or if it gets set back to nil later. This means the class needs to handle the possibility of the dependency being absent, usually by using optionals, var network service, network servicing, and performing nil checks, which adds complexity and potential runtime failures. Also, the dependency usually has to be a var, mutable, which is generally less safe than an immutable let.
Okay. And the third type, which seems used for more localized needs.
Method injection. Here, the dependency isn't provided to the entire object, but is instead passed directly into the specific method that actually needs it.
Like func process order, order data, order payment processor,
Yeah.
payment processing.
Exactly. This is excellent for dependencies that are only needed for a very specific, short-lived operation and don't represent a fundamental requirement for the entire object's existence. It keeps the object's own state and complexity lower by not forcing it to hold on to dependencies it only uses occasionally.
Got it. One final clarification needed here. The difference between dependency injection and a pattern sometimes confused with it, the service locator.
Ah, yes. This is a really important distinction for understanding decoupling. In true dependency injection, as we've discussed, the receiving class is passive. It just declares what it needs, usually via its initializer, and receives those dependencies from some external coordinator or DI container. It doesn't know who provided them or how they were created.
It's given its tools.
It's given its tools, yes. With the service locator pattern, the class takes a more active role. Instead of receiving dependencies, it holds a reference to a central registry object, the service locator, and actively asks the locator for the dependencies it needs whenever it needs them. Like, let network service, service locator.share.get network service.
Why is that considered less ideal than DI?
Because it introduces a hidden dependency. The class looks like it might be decoupled because it's not creating real network service directly, but it's now tightly coupled to the service locator itself. Every class using the locator depends on this global or shared registry. This makes it harder to see a class's true dependencies just by looking at its interface, its initializer or properties, and it makes testing potentially trickier, as you might need to configure or manipulate the global service locator state before your test can run correctly. DI, especially constructor injection, makes dependencies explicit and promotes better decoupling.
Okay, we've covered the big architectural blueprints and the foundational solid principles. But within any architecture, we constantly encounter smaller, recurring problems in how we structure code or manage interactions. That's where classic design patterns come in. They're like the specialized tools in the architect's toolkit.
Exactly. These aren't architectures themselves, but reusable solutions to common problems that help you implement your chosen architecture more effectively and cleanly. They provide a shared vocabulary for developers. ## 6.1 delegation versus closures versus notifications.
Let's start with patterns for communication between objects, which happens constantly in iOS. We need ways for one object to tell another object that something happened or to ask for some data. Delegation is probably the most fundamental iOS pattern here.
Oh yeah, delegation is baked into the core of UIKit and other Apple frameworks. Think UItable view delegate, UI text field delegate. It's fundamentally a one-to-one communication mechanism defined by a protocol.
One object, the delegate, agrees to handle certain tasks or respond to events on behalf of another object, the delegator.
Precisely. It's strongly typed because the communication happens through the methods defined in the protocol. It promotes loose coupling because the delegating object only needs to know about the protocol interface, not the concrete class of its delegate. The crucial thing to remember, always, is to declare your delegate property as weak. Weak var delegate, my delegate protocol, to prevent retain cycles.
Right. Memory safety is key there. What about closures or callbacks? They offer a lighter weight alternative sometimes.
Yeah, closures are fantastic for simpler, often more localized callbacks. Instead of defining a whole protocol for one callback method, you can just pass a block of code directly. They're concise, very flexible, and easy to implement inline.
But they come with their own memory management caveat, right?
They do. They carry probably the highest risk of accidental retain cycles if you're not careful. By default, a closure captures any external variables it uses, including self, strongly. If the object self holds a strong reference to something that holds the closure, and the closure holds a strong reference back to self, boom, you have a retain cycle and memory leaks. Developers absolutely must remember to use a capture list like weak self or unowned self, if appropriate, inside the closure body when referring to self to break that potential cycle.
Okay, so delegation for more formal one-to-one contracts, closures for simpler callbacks with careful memory management. What about Notification Center? When does that come into play?
Notification Center provides a one-to-many broadcast mechanism. It allows an object to post a notification about an event without knowing who, if anyone, is listening. And multiple other objects throughout the application can register themselves as observers for that specific notification name and react whenever it's posted.
Like system-wide events.
Exactly. It's ideal for broadcasting system-wide events where the sender shouldn't need to know anything about the potential receivers. Things like UI application.do become active notification, or maybe a custom user did lodge notification. It achieves maximum loose coupling because there are no direct references between the sender and the observers. The trade-offs are that it's not type safe. Notifications are usually identified by strings or static notification, name objects, and the payload is often an untyped user info dictionary. And tracing the flow of events through Notification Center can sometimes be difficult to debug in a large application.
So delegation, closures, Notification Center. They all relate to this broader observer pattern concept.
Yeah.
And the critical takeaway across all of them seems to be vigilant memory management.
Absolutely paramount. Whether you're using weak for delegates, weak self-enclosures, or remembering to remove observers from Notification Center, though this is less critical with the modern block-based APIs, failing to manage the references correctly in these observation patterns is one of the most common sources of memory leaks and crashes in iOS apps.
Okay, shifting gears to creation patterns. These deal with how objects get instantiated, especially when the creation process itself is complex. Let's talk about the builder pattern. When is this useful?
The builder pattern is designed to separate the construction of a complex object from its final representation. It's incredibly useful when you have an object that requires lots of configuration settings or has many optional properties that need to be set up step by step.
Instead of a massive initializer with 10 parameters, most of them optional.
Exactly. That becomes unreadable and error-prone very quickly. With the builder pattern, you use a separate builder object. You call a series of descriptive, often chainable methods on the builder to configure the object piece by piece, like set catch policy about reload ignoring local cache data, then set ctp method .post, maybe .add header field, accept value.application.json. And only when you're done configuring, you call a final.build method on the builder, which then constructs and returns the fully configured immutable object like a complex URL request or maybe a configured analytics event.
So it makes the configuration code much more readable and prevents those monster initializers.
Got it. Now what about the factory pattern? How does that help with object creation?
The factory pattern provides an interface, often a method, the factory method, for creating objects, but it lets subclasses, or the factory method's implementation itself, decide which concrete class to actually instantiate. The key idea is that the client code calls the factory method instead of calling a specific class's init directly.
Why would you want to hide the init call behind a factory?
It encapsulates the object creation logic. Imagine you have a content manager that needs to display different types of UI view controller based on the type of content item, e.g. article view controller, video view controller, gallery view controller. Instead of having a big switch statement inside the client code to decide which controller init to call, you'd have a view controller factory with a method like make view controller content item. The factory encapsulates that switching logic.
So if you add a new content type later, say podcast view controller, you only need to modify the view controller factory. The client code that calls the factory doesn't need to change at all. It makes adding new types easier and keeps the creation logic centralized and separate from the client code.
Moving on to behavioral patterns. These focus on how objects interact and distribute responsibilities effectively. The strategy pattern seems like a really powerful way to eliminate big conditional if-else or switch statements.
It absolutely is. The strategy pattern defines a family of algorithms, or strategies, encapsulates each one into a separate object, and makes them interchangeable at runtime. The client object holds a reference to a strategy object via a common protocol and delegates the algorithmic task to it.
You mentioned payment processing earlier. Is that a classic strategy example?
Perfect example. Instead of having a payment manager with a giant switch statement inside its process payment method, checking if payment type.creditcard, else if payment type.paypal. You define a payment strategy protocol with an execute payment method. Then you create concrete classes. Credit card strategy, PayPal strategy, Apple Pay strategy, all conforming to the protocol. The payment manager simply holds a current strategy. Payment strategy and calls current strategy.execute payment. You can easily swap out the current strategy object at runtime to change the payment behavior without modifying the payment manager itself.
Very clean. Okay, what about the command pattern? You mentioned it relates to how UI controls work in iOS.
Yeah, the command pattern encapsulates a request or an action as an object. This allows you to parameterize objects with different requests, queue requests, log them, or even support undoable operations.
How does target action fit this?
Think about a UI button. When you set its target and action, button.add target self action, hashtag selector did tap button for .touchup inside, you're essentially configuring a command object implicitly. The button, the invoker, holds on to the information about the request, the selector action, and the object that should handle it, the target. When the button is tapped, it executes that encapsulated command by calling the specified selector on the target object. This decouples the button, which only knows that an action should happen, from the object that actually performs the action.
So it separates the what, the request, from the who, the receiver, and the when, the trigger.
Exactly. It's a fundamental pattern for handling events and actions in a decoupled way.
All right, last category, structural patterns. These deal with how classes and objects can be composed to form larger, more flexible structures. The adapter pattern sounds like a bridge builder.
That's a great analogy. The adapter pattern acts as a bridge between two incompatible interfaces. It converts the interface of one class, usually one you can't change, like a third-party library or legacy code, into an interface that the client code expects to work with.
So if I integrate a shiny new logging library, but my whole app is currently calling methods on my old custom logger class interface,
you'd create a new logger adapter class.
Yeah.
This adapter would conform to your existing logger protocol, the interface your app expects. Internally, the adapter would hold an instance of the new logging library. When your app calls the old log.error message method on the adapter's implementation would translate that call into whatever the new library requires, maybe new shiny logger.recordlevel.severe message at message. Your existing application code doesn't need to change at all. It just interacts with the adapter as if it were the old logger.
It's like a universal translator for code interfaces. Okay. And finally, the facade pattern. What problem does this solve?
The facade pattern provides a simplified, unified interface to a larger, more complex subsystem. It hides the intricate details and interactions of multiple components behind a single, easy-to-use front door.
Like simplifying a complex system.
Precisely. Imagine you have a complex video processing subsystem with separate classes for video decoder, audio extractor, subtitle renderer, and output encoder. A client wanting to perform a simple transcode shouldn't need to know about or manage all four of those components directly.
Sounds messy.
It would be. So you create a video transcoding facade class. This facade might expose just one simple method, like transcode video, input file.url, output preset. Internally, the facade's implementation would coordinate all the necessary interactions between the decoder, extractor, renderer, and encoder. The client code just talks to the simple facade interface, completely unaware of the underlying complexity it's managing. It reduces dependencies and makes the subsystem much easier to use. Hashtag tag outro.
Wow. Okay, that was an incredibly deep dive. We really covered the gamut. We started right at the beginning, identifying that fundamental flaw in classic iOS development, the massive view controller problem rooted in plain MVC.
Yeah, and from there, we charted that whole evolutionary path. We saw how patterns like MVVM and MVP emerged specifically to pull presentation logic out of the controller, aiming for better separation and, crucially, better testability.
Then we explored the heavy hitters for large-scale complexity, the strict separation enforced by Viper, and the dependency-inverting layers of clean architecture, both designed for those massive, long-lived enterprise applications where maintainability is paramount.
We also looked at the modern approach to start management with PCA, focusing on predictability through unidirectional data flow, pure functions, and explicit actions, even with its associated learning curve and boilerplate.
And maybe most importantly, we grounded everything in those foundational principles.
Right.
Solid, especially single responsibility and dependency inversion, and the practical mechanism of dependency injection that enables them. Plus, we touched on that essential toolkit of design patterns: delegation, closures, factory, strategy, adapter, facade. the building blocks you use within any architecture.
Yeah, and I think the final takeaway for you, the listener, always comes back to trade-offs. There's rarely one perfect architecture. The choice between these patterns is always a balancing act. You're trading off things like initial setup complexity, boilerplate, versus long-term testability and maintainability. You're balancing simplicity against scalability.
So MVVM often feels like that pragmatic sweet spot for a lot of modern iOS development, especially with Combine and SwiftUI.
It often does, yeah. But when your application's complexity reaches a certain threshold, or when absolute predictability and testability become non-negotiable, investing in the rigor of clean architecture or the functional purity of TCA might be the right call, despite the higher initial cost. The best architecture is ultimately the one that most effectively helps you manage the specific complexity profile of your particular application over its lifetime.
That makes a lot of sense. Okay, that brings us to our final provocative thought for you to chew on after this deep dive. We spent some time discussing dependency injection and established that constructor injection is generally preferred in Swift because it guarantees that dependencies are non-nil upon initialization, making objects inherently safer and their requirements explicit.
Right. The safety guarantee is a big win.
So the question is, given this robust safety advantage of constructor injection, does this effectively render the other main type, property or setter injection, obsolete in modern Swift? Or are there still specific legitimate edge cases or perhaps unavoidable trade-offs within the iOS ecosystem? Maybe situations involving complex object graph creation, lifecycle issues, or interactions with certain older UIKit components or storyboards that would still necessitate, or at least justify, the use of property injection, despite its potential downsides.
When can't you control the init method directly? That'll be a good place to start thinking.
Exactly. Something for you to mull over. Thanks for diving deep with us today into the architecture of building better, more maintainable iOS applications. We'll see you next time.